Welcome back, y'all. In this video, I'm going to be making chloroacetic acid, also known as monochloroacetic acid or MCA. I ran into some difficulties with the reaction in the urinal cake series, so I decided to try something relatively simple that wouldn't take long. I'm making MCA for another project, but I also wanted to test out the reptile lamp setup as a source of UV light for photocatalytic reactions. There are a few other UV catalyzed reactions I've been interested in trying. I just never had a good UV light source. I've seen other channels, specifically Chemulus and Extractions and Ire, in their cubane syntheses use LED UV lights for one particular step, along with other channels for various experiments. I looked at the lights they use, and as far as I can tell, the light provided by them is generally from 365 to 395 nanometers. I don't have anything against LED UV lights, but historically, all the literature I've read, which is admittedly somewhat limited, has used mercury vapor lamps as UV light sources. Maybe the vast majority of modern photocatalytic research chemists use LED UV lights exclusively, and I'm out of touch, I don't know. Mercury vapor lamps are used as UV light sources because they give off radiation intensely in the UV region as far down as 254 nanometers. Again, I don't know enough about photocatalytic reactions to know if there's a most active region of ultraviolet light for reactions. That is, if it's even consistent across different substrates. I just had a hunch that a mercury vapor lamp would be better than the LED panels. If you're a photochemist watching this and would like to clear things up for me, let me know in the comments. As a side note, I'm well aware that quartz glass would be the ideal material for apparatus in UV catalyzed reactions as it transmits UV light super well, but it's expensive, fragile, and borosilicate glass transmits UV light well enough for my purposes. MCA has a lot of uses, the biggest being to produce the thickening agent carboxymethylcellulose and carboxymethyl starch. It's used in the production of some herbicides, epinephrine, and thioglycolic acid. And it causes severe chemical burns. If you go on the Wikipedia page for it, there's a very nice picture of that if you want to see. I just don't want to post it on my channel. I used 12 grams of red phosphorus, 150 grams of acetic acid, and enough TCCA and hydrochloric acid to produce 2.5 moles of chlorine. I could very easily have used a lot more chlorine, but I wanted to minimize the production of dichloro and trichloroacetic acids. The procedure that I'm basing mine on used sunlight as a source of UV light because it's from 1947, I want to say. And they basically bubbled chlorine through the reaction mixture for a day in the summer or 2 days in the winter. Enough yapping, onto the video. There's the red phosphorus. Then there's the acetic acid. Here's the mostly assembled setup, and here's the light I used. It looks like a normal light when it's on because it gives off visible light in addition to UV light and heat. So I did a whoopsie by starting the chlorine generator without realizing the stopcock of the gas outlet was closed, so it popped off. Teehee. Luckily, I did it before putting the joint clips on all the joints. The reaction vessel is heated by a boiling water bath and equipped with a condenser. When the chlorine is let into the reaction mixture, there's a lot of HCl being produced because the phosphorus trichloride formed by chlorine reacting with the phosphorus immediately reacts with however much water is left in the glacial acetic acid. It's super annoying to make anhydrous glacial acetic acid, so I didn't bother. Once all the water reacted, the HCl fumes more or less disappeared or were minimal enough that they didn't fume in the air, visibly. The chlorine addition took 2 hours and 15 minutes total, much better than the full day or 2 days of sunlight in the literature value, and I did have to replenish the water a few times. I could smell acetic acid throughout the run of the reaction, which explains something later on. The reason for this is the lamp heated up like half of the condenser since it also radiates heat, so some acetic acid escaped instead of refluxing and staying contained. Chloroacetic acid boils at a much higher temperature than acetic acid, so I'm going to assume none of it escaped the reaction vessel. Once it got dark, the light also attracted hella moths to their agonizing demise by being boiled alive. Moths were most definitely harmed in the making of this video. After it cooled down, I stoppered the condenser and let the reaction mixture sit overnight. Then I set up for a short path fractional distillation. Chloroacetic acid boils at 189 degrees, so it was necessary to insulate the column and boiling flask with aluminum foil. An air-cooled condenser was used because chloroacetic acid is a solid at room temperature with a melting point of 63 degrees. I'm using the same bottle from my trial run of the reaction to collect the unreacted acetic acid fraction. In that run, I gradually raised the temperature of the heating mantle, but in this one, I just maxed it out, and the acetic acid came over pretty warm this time. I'm sure I lost some because of this, but acetic acid is cheap for me, so I don't mind. Once the temperature reached 150 degrees, I started collecting the second fraction. The procedure, this is based on collecting the fraction up to 200 degrees, but the temperature never rose past 186 degrees. The literature boiling point, like I said, it's 189 degrees, but where I live, the elevation is about 3,000 feet, so pretty much everything boils slightly lower than the reported values. Here's the second fraction, a little over 60 milliliters of chloroacetic acid contaminated with some acetic acid. It's liquid because it's supercooled until I just picked the beaker up and it immediately began to spontaneously crystallize, which I wish I got on camera, but it happened too quickly. Once I felt it had cooled enough, I hurriedly crushed the chunks in a mortar and pestle and began to filter the mixture. This is the same fractional freezing technique I used to purify the PDCB in a previous video. The liquid I don't want, the solid I do. As you can see, there was a considerable amount of liquid in the mixture. After running the filtration overnight, I transferred the filter cake to 2 coffee filters that had a few paper towels folded in half under them to wick off the remaining acetic acid adhering to the crystals. This worked fairly well. I could have done it again and gotten the last bit out, but I didn't. So here's what I ended up with. 51.55 grams of chloroacetic acid damp with acetic acid. I assumed about 5% by weight was acetic acid arbitrarily and calculated my yield based on this. The acetic acid had 20.73% chlorine absorption based on the starting acetic acid, assuming 2.5 moles exactly of chlorine were generated. I determined the melting point to be 58 to 63 degrees, which is close enough to literature, given the presence of some acetic acid. 62 grams of presumably acetic acid, but probably some chloroacetic acid too, was recovered in the combined distillation and filtration, so approximately 1 mole or 60 grams of acetic acid was lost during the course of the reaction, like I mentioned earlier, because of the heating of the condenser by the lamp. And that's about everything I've got. Thanks for watching. If you want to, like, comment, and/or subscribe, and I'll see you in the next video.